Okay, so did your work look a little something like this? How'd you do? Yeah? Did you check your answer, right? You graphed the original, you graphed its derivative. You then graphed your answer right here. And you graphed it right on top to see if it matched up with the derivative. Okay? And then there's a few ways you can find f prime of 3. I'd say the easiest way is on your calculator, numerical derivative at a point, then use or 1, type in what you're evaluating it at, type in the original, and it'll get the equal for you. Okay? Sounds good? All right. Here we go. So let's talk a little bit about derivatives, okay? So dy dx is a noun. It means the derivative of y with respect to x. When you calculate the derivative of a function that looks like y equals, the answer looks like dy dx equals. Whereas d dx is a verb. It necessitates a command. It's like, hey, can you take the derivative of this thing? And you're like, sure, of course. So d dx is notation telling you that you need to take a derivative, whereas dy dx equals the derivative that you found, okay? All right, so let's kick it off with the power rule, which I feel like a lot of you have already kind of discerned as you watch us calculate some of these limits longhand. So the power rule is, if n is a real number and a is a constant, in the function f of x equals a times x to the n, what do you notice? There's a coefficient out front, x, and then he's raised to a power. So if we can get something into that form, we can use the power rule, which is a really easy way to calculate a derivative. So we want to try to rewrite as much stuff as we can in that form so we can use the power rule. Then the derivative of a polynomial a times x to the n is equal to a times n to the, well, I want this erased. Okay, a times n times x to the n minus 1. What does that mean? That means we took this power, we dropped it down in front, and multiplied it by whatever coefficient was already there. Then we reduced the power by 1. Okay? Equivalently, we can write f prime of x is equal to a times n times x to the n minus 1. That's just saying drop the coefficient down, reduce the power by 1. That's all the power rule is. Okay? It is in your formula booklet at 5.3. If you want to open it up and just look and see where all the derivatives are located, that could be useful right now. But this is just the power rule. The constant rule is the same thing as the power rule, right? Because what is a constant? A constant is 5 times x to the 0, right? Where x to the 0 is 1, so we just have plain old 5. So if I dropped that 0 down in the front and multiplied 0 times 5, it wouldn't matter what came next to it. The derivative of a constant will always be 0. And that's because the power of 0 dropped down and multiplied by the front, okay? If you want to think about it in a more mathematical sense, right? A constant function, for example, y equals 5, is a horizontal line whose slope is 0, right? So if you drew a tangent line at anywhere along the curve of that flat line, what's the slope of the tangent line going to be? 0, right? Therefore, it follows that the derivative of a constant function is 0. That is, if c is an element of all reals, then the derivative of c is equal to 0. We can use the power rule whenever there is a coefficient with, I wrote this all yesterday, so this is like my thoughts. We can use the power rule whenever there is a coefficient with a variable raised to a power. If you can rewrite a function in this structure, you should. Why? Because the power rule is easy to use. The power rule can be used to find the derivative of. Okay, here are the 3 major structures that we, oh my goodness, I'm sorry. Here are the 3, I was writing some letters of recommendation. Here are the 3 major structures. Was that one yours? Oh. So there are 3 major structures that we use the power rule for. Polynomials, so a very classic example would be calculate the derivative of, and then you have something that looks like this. 6x to the 5th plus 9x squared plus 8 over x.
Wait, what is that little thing? Can you zoom in? Yeah. Is that dx? It's an example.
It says example, and then it's d dx. So your first step is going to be to rewrite all terms as coefficients, or just coefficient times x raised to a power. So I have 6x to the 5th. He's fine. I'm not going to change him. I have 9x squared. He's fine. I'm not going to change him. I should rewrite the 8 over x. I should rewrite that as 8 times x to the negative first. Now I have coefficient x to a power. Do you see how you would need to rewrite something like this so he is in a usable form for the power rule? Yeah. Okay. Now you're going to differentiate. To differentiate. That means to take the derivative of differentiate. So here's how we would differentiate something like that. I would have 5, bring it down. 6 times 5 is 30. Reduce that 5 by a 1. I now have 30x to the 4th. Plus 2 drops down and I get 18x. Reduce the power by 1. It's just plain old 18x. Negative 1 drops down. I have negative 8x to the negative 2nd. You're now going to want to rewrite that, guy, so you have no negative powers. And you have 30x to the 4th plus 18x minus 8 over x squared. That would be the derivative of something like that. There are other ways that you would want to use the power rule, but they all kind of anchor into the same idea. You want to rewrite it as coefficient x to a power. So if you had another example that looked like this, take the derivative of 8 over x cubed. Now in this category, we are calling them radical functions rewritten with rational exponents. So this lumps radicals in there, but in this case, we're going to turn this guy into a negative exponent, okay? So it's basically just you practicing rewriting weird looking things as coefficient x to a power, okay? So step 1 is going to be the same as the step 1 over to the left. Rewrite all terms as coefficient times x to a power. So this guy would get rewritten as 8x to the negative 3rd, okay? Then I would take the derivative of that. I would drop the negative 3 down in the front and multiply it by the 8. So I get negative 24x, reduce that power by 1, negative 4th. I'm now going to rewrite him with no negative exponents. Negative 24 over x to the 4th. Pretty easy, right? There is a third and final way that we can rewrite scary things to try to use the power rule because it's the easiest. The other scary scenario over here is rational functions where the denominator can be split up. So for example, we would have something that looks like this. X squared plus 6x minus 3 over x. So what you would do here is, you know when you have, x squared over x plus 6x over x minus 3 over x, and you wanted to combine all of those, you would just do all the stuff in the numerator and they already have a common denominator. So you're basically just taking this and working backwards. You're decomposing it. You've done this your whole mathematical life when you were adding fractions with like denominators, okay? You're just now working backwards and decomposing. It's called fraction decomposition. And it's very useful now and in integrals and all sorts of stuff, okay? So step 1 is going to be the same as those other 2 step 1s. You're going to try to rewrite everything as coefficient times x to a power, okay? So let's rewrite that. And the way we do that is you're going to split this all up. So I've got the derivative of x squared over x plus 6x over x minus 3 over x. Now you're going to want to try to simplify before you take the derivative of it, right? X squared over x will reduce to x, 6x over x will reduce to 6, and then negative 3x to the negative first will be written like that. Notice how we have not taken the derivative yet. Sometimes kids do the rewrite and they forget that they didn't take the derivative yet, right? So keep the notation kicking around so it can kind of inform you of what you have to do next. Okay, I still see a d over dx with brackets, so that tells me that I still have to take the derivative of this. When I, step 2, differentiate and take the derivative of this, I will now have the derivative of x, plain old x is just 1. The derivative of 6 is 0. And I'll now have plus 3x to the negative 2nd let's rewrite that as 1 plus 3 over x squared. Okay, so 3 tools all stemming from the same rule, power rule. You can split up rational functions, but not always. Not all rational functions can be split up like that. Can you split up something, or let's write this, non-example. Can you split up something that looks like this? No, right? You need to have a bunch of things in the numerator over one common denominator. That's the only way you can decompose it. Yeah? Okay. Okay. Let's go to some practice problems, okay? Find the derivative of the following function. So the directions are in, or the directions are in, they're written, so we don't have the d over dx. But sometimes you have it, sometimes you don't. You just have to read the directions. So I wanted you to see both cases, right? So find the derivative of the following functions. The derivative of y equals 8, super easy. They gave it to you as y equals, so your answer should look like dy dx. The derivative of y equals 8 is, good job. All right, what should this guy look like? He is f of x, so we have f prime of x is equal to, what's the derivative of 0? 0. All right, s of t, s prime of t. The derivative of 3 should be what? 0, boom. Y equals k times pi squared, where k is the constant. What should dy dx be in this case? 0, good job, right? That pi trips you up. He's not a variable. K is a constant. This whole thing would end up being a constant, right? Okay, let's take the derivative of e. F prime of x, we have 3 times 2 because that 3 is getting brought down. So we've got 6x squared plus 10x, reduce the power by 1, and then the negative 3 drops off. F of x is equal to x cubed minus 4x plus 5. Let's find the derivative, f prime of x. That'll be 3x squared minus 4. All right, we really want everything to be in coefficient x to a power. What do you think we need to do in order to get this guy into a usable form? What should we do with this one first? You should expand, okay? And then we're going to get everything as one long string of a polynomial, and then we'll take the derivative. Go ahead, try to do this one on your own. See how you do. And use your notation, right? Keep writing y equals until you actually take the derivative, or you might get confused as to when you took the derivative or did not. All right, once you've expanded, you should get a polynomial that looks like 9x cubed plus 12x squared plus 4x. Now, let's take the derivative of this together, okay? So I have 9 times 3 is 27x squared plus 24x plus 4. Power rule is so easy. We love the power rule. All right. In the middle column, remember, the middle column are practice problems where we can use the power rule, but we now have radical functions rewritten with rational exponents, or fractions and they're rewritten as negative exponents, okay? But we still want to get it as coefficient x to a power. So let's try to do letter A, okay? So in letter A, whoo, okay, stop. I want to try to split off the coefficient first, right? So I have a 1/3 out front, right? Coefficient, x to a power. Yeah? Okay, now I can take the power rule. Perfect. Or use the power rule, whatever. So now I'm going to do 1/3 times 1/3 gives me 1/9 x to the 1/3 minus. Okay, let's do this smart. I have to subtract a 1. What would be a smart version of 1 to make this calculation easy? 3 over 3. Good job. So I've now got 1/9 dy dx equals 1/9 x to the, okay, 1 minus 3 is going to give me negative 2/3. You're going to want to clean that up. Dy dx is equal to, okay, so I'm going to have 1/9 times, who's feeling brave? What can we do for this guy? Cube root of x squared. Good job. All right, let's try one more. I want to try to get coefficient times x to a power. Coefficient times x to a power. 1/x to the pi. If we want to bring him up out of the denominator, wouldn't it be x to the negative pi? Now we have check, right? Coefficient times x to a power. Yeah? We're good. All right, so I'm going to bring that exponent down, and I have negative 5 pi over 3 times x to the negative pi minus 1.
Wait, so does the negative pi go to all of it?
This one, I mean, like, I kind of just wanted to illustrate an idea, but technically, I guess if you wanted to make this positive, you would have to be like 5 pi over 3. Then you have x to the negative 1 pi plus 1. So then now you would have like negative 5 pi over 3x to the pi plus 1, if you wanted to write it all as like one positive exponent. But I kind of just wanted to show you how to work with pi's. But if you, yeah, sure, here we go. There we go, that's the answer.
Wait, I'm so confused. This was not what I was asking at all.
Oh, you could have stopped here or there, it's fine. What were you asking?
Because you didn't like write the thing as parentheses, so is the negative pi over the exponent like that? Is it going to both the 5 pi over 3 and the x?
No, he's not in parentheses. That's a great question. If the 3, so like if you had parentheses that were like this, then yeah, that pi better go to both of them. But he's just going to the x because there's no parentheses there.
So then why did it become negative 5 pi over 3?
Because x was raised to a negative pi. So when I brought him down and like multiplied him by the coefficient out front. Right? So it was like 5 over 3 times negative pi over 1, essentially. Yeah? Okay. Maybe we should put that one towards the back at the end. Put it at the end. Next year. All right, so let's try this one. All right, so we've got d dx of, try yourself to see if you could put this guy in coefficient x to a power. Then we'll take the derivative together, okay? Yeah, 6 times x to the negative 3/5. Boom. Okay, do coefficient times power and reduce it by 1. See where you get. Oh, this one's ugly too. All right, got to think for this one. Negative 18 up top. I got a 5 out front, and then I'm going to do 5th root of x to the 8th. I don't want you to mess with like trying to pull out like, you know, remember how we did that in the past where we're like, let's get all the full roots out from the denominator. We don't have to do that. Just leave it like this. I just want you to practice. Okay. You would break this up into like the 5th root of x to the 5th times the 5th root of x to the 3rd, and then pull it out. Remember? Yeah, we don't have to do that. Okay. So let's try D. Okay, what is the coefficient? Here we go. What's the coefficient? Yes. What is, x to the radical 2 power, but he's in the denominator. What should I change him to? Who's feeling saucy? X to the negative. Good job. Okay, perfect. Trust your gut, right? Same old jazz. We got negative 5 rad 2 over 2 times x to the negative rad 2 minus 1. I don't need you to further simplify. This is fine. We're just practicing. You could factor out a negative 1, drop that power down below, make it positive. We're good. This is fine. Okay. Let's look at E. What is the, ooh, this is just like what Jordan was asking me about earlier. Jordan, what do you think? I'm going to give this 3 to each term in the parentheses. I am now going to have 4 over 2 to the third, x to the third. That's going to be like a 4 over 8x to the third. What should we do now? Yeah, for sure. What do you think the coefficient should be? 4 over 8 or 1/2 for sure. I just want to work with less numbers, right? And then what about the x to the third, but in a denominator? X to the negative third, right? Okay, let's find the derivative. Okay. All right. Okay, you ready? Here we go. How many more? Oh, not bad. Okay. Yeah. All right, F. Try F. Pull out the coefficient. What is it? 7 over 3. What do you think you should do with the t over radical t? Don't you want to get it as all one power? Right? So it should be t to the first minus 1/2, right?
Wait, when I put the negative, what is that minus, like, being our negative?
Yeah, check it out, right? When you divide like powers, what do you do with the exponents? So you should have t to the 1 minus 1/2, right? Okay. Yeah. Okay. So now, that's it. Yep. Okay, so now we've got 7 over 3 times t to the 1/2. Okay, let's find the derivative. Oh, dt, excuse me. Okay. So now we've got 7 over 3 times 1/2 is going to give me 7 over 6, right? Times t to the 1/2. Let's take off a smart version of 1. So we now have negative 1/2. All right. Then let's drop him down into the denominator. 7 over 6 square root of t. Okay. All right, let's do the last one. Oh no. There are many, many, many different ways to think about this. I want you guys to try to the best of your ability to get this as coefficient, variable, power, and then take the derivative, okay? And then you can look at mine when you're done and see how you did, okay? Go try to do it on your own, okay? Okay, there we go. Stop. What is it doing? Stop that. What is it? DM? D. All right, who got this right? Who's still working? Okay. Who didn't raise their hand? Who has a belly button? Oh, you guys failed. Well, when you have a negative exponent in the denominator, what does that mean? Move it to the numerator and make it positive. Okay.
Wait, did you change what?
Not really, because I'm not dividing. It's just like the 3m squared, he was raised to a negative second. So I kind of pulled out the -1, because then I knew that if I had a negative exponent in the denominator, the only way to make it positive is to flip it up top.
If it's negative on the top, you can put it on the bottom. If it's negative on the bottom, you can put it to the top.
All right. Let's try some where we split up the denominators, all right? This guy, we're not really splitting up the denominators, but I wanted to see if you were thinking. Here we go. I've got g of x is equal to, what do you think you should do with that negative x to the fourth over 2? You should peel that negative 2 to the front so he's a coefficient and it makes the math easier to see, right? Oh, I just rewrote the exact same thing that was written above. Go me. All right, now take the derivative using the power rule. And then make sure you reduce. Okay, try splitting up the next one while I do. Okay. Did you split it up and it looks like this? Something like this? Yeah.
Ours is 17. What?
All right. What?
Ours is 17.
17.
So 1
Minus
is 17.
What?
It's supposed to be a 7.
Like instead of minus 1, it was minus 17.
On yours?
Yeah.
Oh, interesting. Okay. All right. That still works, right? That's weird. I don't know why it does that sometimes. Okay. Does anyone know why it does that sometimes? All right. Okay. So what's going to happen? I've got f of x equals. Okay, so these cancel and I have 6 plus. What about this guy? Good job. What about this guy? Let's do it as 17x to the negative second. Does that work for you?
So then it wouldn't be 3.
Yeah.
The x minus 1.
Yeah, let's change that one too. We could do it in a new line or we could just do this. Is this okay? Is that one okay? Just to kind of save ourselves some space. All right, cool. So now we can take the derivative. Ooh, I don't want a 17 there. That's probably why I changed it. That's all right. Okay, f prime of x. So we've got 0. All right, tell me, what am I writing? Be my voice.
Negative 3x.
Negative 1 minus 1. Negative second. Good job. Okay, keep going.
Plus 34x to negative 3.
Good job. Okay, I'm going to rewrite this a little better. Negative 3 over x squared plus 34 over x cubed. All right. Let's do the next one. I want you to split it up. Can you split it up on your paper? Put everything over the denominator piece by piece. What do you think you should rewrite the radical x as? X to the... Yeah, because you're going to end up combining those powers. Good call. Oh, this is an annoying one. Okay. I've got 3 minus 1/2. Let's see if we can do this in a smart way. The 2's are going to cancel, and we'll have x to the 6 over 2 minus 1/2 would give me what? X to the 5 over 2, right? And then for the next one, I've got a 3 over 2 out front, and then I've got x to the 2. Let's change that to 4 over 2, right? So 4 over 2 minus 1 over 2 is going to give me x to the 3 over 2. Do you guys know what I'm doing? Do you want me to write it out? You're doing okay? All right. And then I've got plus 7 over 2. This is going to be x to the first power, so I'm just going to do it 2 over 2. So it's x to the 2 over 2 minus 1/2 is going to give me x to the 1/2. And then I've got 5 over 2. Oh, this one's kind of funky. Okay, so I'm going to have 5 over 2 times x to the negative 1/2. So this guy's going to have a negative 1/2 out front. So I've got negative 5 over 4 x to the, let me take off one more, negative 3 over 2. Okay. Oh, that one has a derivative done. Okay, so we'll just know that that guy's derivative is done.
Why is it 5 over 4?
Yeah, hold on. I took the derivative at the same time that I was rewriting it. That's confusing. Let's skip that. Let's do 5 over 2x to the negative 1/2. Now we're all even. Okay, perfect. All right, let's take the derivative now. Here we go. All right, these can get a little funky. So I've got 5 over 2. And then minus 2 over 2 gives me 3 over 2. And then I got 9 over 4. Minus 2 over 2 gives me 1/2. 7 over 4 x to the 1/2 minus 2 or negative 1/2. And then this is going to be minus 5 over 4 x to the negative 3/2. Did you do it? Looks pretty gross. We're not going to, no. Yeah, let's just leave it like that. We make the rules. I mean, you would want to make the powers positive if you can, but we're just practicing the scale today, right?
The negative 3 over 2 to the x to the 3/2. Wouldn't that just turn over x to the 1 because it's minus and 1/2? Oh wait, it's minus 1 whole.
Which term are you looking at? First, second, third, or fourth? Oh, you got it? Okay. All right, look at this last little palate cleanser here. Look at this little sweet baby. Here we go. We got x over x plus 5 over x. Boom. Okay, so do you see how even though it's like 3 different looking ways the original problem could look, you're all anchoring back into the same structure where it's coefficient x to a power, so that way you can use the power rule. Yeah? All right. Cool. So, thinking question. What does it look like graphically when the slope of a tangent line to a curve is equal to 0? Well, let me give you a little sketchy poo here, okay? Remember, a tangent line is like I draw it, it touches once. Where do you think a tangent line would have a slope of 0 on this guy? It would be a flat straight line, yep. Where do you think that would happen? The max and the min, good job. Very good. So in these cases, we would denote this as m tan equals 0. The slope of the tangent line is equal to 0. And that happens when there is a max or a min. Let's talk more about the slopes of the tangent lines as we move along the curve, because we know that it changes depending on whatever x we're at, right? We need to know how to write the equations of tangent and normal lines, and here's why. I want you to read this quick little blurb here. This hopefully contextualizes it all for you. Look at this picture that I put right here, and then we're going to do an example problem together, okay? Usually you guys take these notes, but because of the snow day, I had to put 2 days in one. What?
I was confused and I wrote these in my book.
Oh.
I didn't understand because we always have work and then we didn't, so.
Yeah, I figured I could probably just teach it in one day. Okay, go ahead. Read. See you in a minute. me a thumb in the air, please. All right, so conceptually, can we all agree that this is the curve f of x, right? The tangent at this particular x here, the tangent line will look something like this. The normal line is the line that is perpendicular to the tangent line at that particular x. What do you notice about this point and the curve, the tangent, and the normal line? It's a common point. They all share that one point, okay? All right. The way that we can write the equation of the tangent line or the normal line is using slope-intercept form or point-slope form. Since we have, bless you, the slope of the tangent line from evaluating the derivative at that particular x, and we have that one point that they pass through, I would say that using point-slope form is the easiest way, but sometimes they ask you the next structure and then you use that way. But we're going to defer to writing in point-slope form when we write the equations of these tangent and normal lines, okay? All right, let's see what's going on here. So, example 1 says find the equation of the tangent line f of x equals 2x squared minus 6x plus 8 at x equals 2. To find the equation of a tangent or normal line, you need 3 things. And you're always going to set up this little grid for yourself whenever it asks you for the equation of the slope of the tangent or normal line. Point, slope, equation, okay? The way you find the point, you take the point of particular interest. You evaluate the original at that point. You would find f of 2. So in this case, you're going to plug that 2 back into the original. So you have 2 times 2 squared minus 6 times 2 plus 8. F of 2 is equal to 4. The point of interest is 2 comma 4. Why do you need a point? Because you're going to write the equation of this tangent line in point-slope form. Here's your point. Bada boom. Gradient of the tangent line. That's the slope of the tangent line. Remember, IB refers to slope as gradient. You would find the derivative of the original and then evaluate it at that particular x value. The derivative of this guy would be 4x minus 6. I'm going to plug in the 2. And I'm going to have f prime of 2 is equal to 2. And you could check your work with the numerical derivative at a point function on your calculator. Okay? In fact, if it's a calculator question, just plug it in and get it that way. You don't need to calculate the derivative. But sometimes they're not calculator questions, so you do have to know how to do both. This is your m tan. The slope of the tangent line, when x equals 2, is 2. You are going to start with the point-slope equation of a line. Y minus y1 is equal to m times x minus x1. This is x1, this is y1, this is m. Y minus 4 is equal to 2 times x minus 2. This is the equation of the tangent line. Find the equation of the normal line. The equation of the normal line is going to be of the same curve at the same point. So what do we know about that common point up there? This is a graphical representation of everything that we just found, right? What do we know about that point that the normal, the tangent, and the curve pass through? It's that same point we found up here, so we can just use that same point again. Except now, for a normal line, the gradient will change. We will now have the negative reciprocal of the tangent line will be the slope of the normal line. We still plug it into the same structure. That's the equation of the normal line. Now anchor back in what you learned with the picture over here, okay?
Wait, why would you not like add the 4 in?
More work. They're equivalent representations of the same thing.
Wait, I'm confused.
What did you just do?
What, 4x plus 16? 4x
What?
minus
Go ahead and
I
expand
get
it.
what she just did, I don't understand what it's finding.
This is the equation of, this is the curve, right?
Yeah.
Walk with me, this is the curve. This is the point 24, right? This is the tangent line. The equation of the tangent line, it made me approximate it because I was using the geometry function, which is like kind of crummy. But if you distribute all this out in combined like terms, I promise that you would get y equals 2x.
Yeah.
That's the equation of the tangent line at that point. It approximated because it's annoying.
Where did 4x minus
The-
6 come from, the gradient?
4x minus 6.
And the gradient of m.
Very good. We took the derivative of the original and evaluated it at the point of interest. That returns the slope of the tangent line when x equals 2.
The gradient derivative are the same thing.
Gradient, slope, derivative, all the same thing.
Where did you?
And then this is the equation of the normal line. This, it's like, it's clunky. I can teach you at the end if we have time, but look, it like approximates it. It's like a way for me to show you as a math teacher, not so much for you to check, because would you know that this is the 2x and it's supposed to be 2x? Like, you know what I mean? It's just a way that I can show you what you're calculating.
So
Yeah.
the negative reciprocal is like negative 1/2 over.
It's the negative reciprocal is like if you took 2 and you put it over 1 and then you flipped it and negated it.
So you plug that in instead of.
That's the slope of the normal.
That's the slope of the normal line. Yep, he's going to go where m goes in this point slope formula of a line.
How do you know that?
How do you know what?
That it's the slope of the normal line.
Because it's a perpendicular line. So how do you calculate the slope of a perpendicular line? You find the negative reciprocal, right?
So
Yes.
So it's just a negative. So it's negative 1 over whatever the slope is.
Yep. As written up here, right? Check it out. Negative reciprocal. M norm is equal to negative 1 over M tan. Okay. All right. Let's check out the next one. Here we go. It says write the equation of the tangent line. So I set up point, slope, equation. PSE, right? Please stop eating. That's me every day. Please stop eating. Okay, so the point, what's the point? I'm taking x equals 1 and I'm plugging it into the original. Go.
Honestly, I don't.
Okay. 1 to the 6th is 1. 1 to the 3rd is 1. 1 minus 1 is 0. All right, the tangent. How do we find the slope of the tangent line? We find the derivative of the curve. 6x to the 5th minus 3x squared. I now evaluate the derivative when x equals 1, f prime of 1. I can type this into my calculator and find it. What's up?
That derivative
Uh-huh.
is what we did on that.
Yeah.
Wait, so
And
also,
what is the other way we find derivative? What are
That's the limit
like
definition of the
first step?
derivative, which is like the mathematically fancy concept that this is all rooted in. It's basically just saying the instantaneous rate of change is you
As
shrinking the distance between the 2 points of a secant line until they're
Okay,
meeting.
so this is actually how you.
So that's actually how you find the derivative.
This I was just
Yeah.
like,
The other one was just like
Let's say it was
rooting it in what you understand.
So it's just like more
Okay.
concept.
Yeah.
So that really has nothing. Okay. Okay.
Essentially. Well, no, it's not that it doesn't have anything to do with it. It's just like that way is so clunky,
Yeah.
right? Imagine doing x plus h to the 6th minus x plus h to the 3rd. Bye. Right? So that's why we invented this. Okay. So now we have 6 times 1 to the 5th minus 3 times 1 squared. So we have f prime of 1 is equal to 6 minus 3, which is 3. So I now have the slope of the tangent line is 3. Put it all together. Copy down your structure. I don't want to see all you people that think you're too good for the original structure. Just write it down. Ooh, what it goes in for m? I forgot to put it in. 3. So now I have 3x minus 3. You could expand it out. You don't have to expand it out. You could perfectly leave it as this. You could perfectly leave it as this. Totally fine. But I feel like this is probably one that we could envision, right? Like, what does that line look like?
What happened to the negative reciprocal?
Well, it's asking us for the tangent line. This is the tangent line. Now we're going to find the normal line. All right? That's the tangent line. Now let's find the normal line. So the normal line is going to be the exact same kind of thing, right? Y minus 0 is equal to. And then, Jordan, you tell me what's going to go in here for the slope of the normal line. Yes. Boom. Okay. So let's envision this on the graph. This is us checking, is the slope of the tangent line 3? It is. Then we graph it all. Whoa, what a nightmare, but that's okay. Check it out. Original curve. Funky little draggy U. And then right here, when the point is 1, 0, right? This one actually found the correct tangent line. Go computer. So it's 3x minus 3, which is exactly what we got over there. And then the equation of the normal line is right here, which you can type in relation mode if you are feeling lazy like me. All right? Do you see what you're finding now, right? Let's say you were like building a roller coaster and this is like the bottom of the roller coaster, right? You would need to know the force that's coming off in this way, the force that's going in on that way, right? So this is like how you would start to set up the trajectories of things, right?
I I get the whole, like, that's what you're finding the force, but what actually is that?
What is what?
Like, in the thing, and what you just said, it's like that line, is it just like what the slope of that line is the force at that point in the curve?
Okay, so the slope is the instantaneous rate of change at that point, right? And then the tangent line or the normal line shows like how the force can be like extrapolated as time goes on. Does that make sense? Where's the force going?
We need to take two.
It's like a model of how things are moving. Does that make sense? Right?
We didn't take two.
No idea.
I had to take two.
All right, let's do the next one. Go ahead. The next one, do you know how to find the derivative of something that looks like that? No. So what do you think you should use to find the derivative of? Yes, very good. So let's find the point. So we've got f of 2. That's going to be 3 over the square root of 7 times 2 minus 5. F of 2 is equal to, so it's going to be 3 over 14 minus 5, which is 9, 3 over 3, which is 1. Okay, so I've got 2, 1. That's my point. Slope of the tangent line. Go ahead, plug it in. What would we get? We would do menu 4, 1. Type it in. And we would get m tan is equal to negative 7 over 18. Let's find the slope of the normal line. Okay, this one's a little funky. What do you guys think the slope of the normal line would be? We flip it, and then we negate it, making it positive. Good job. Now let's write our equations. So easy. What's up?
So like, if you were to find like you just do like the menu for one, and you get like the derivative, how do you know what the slope of it is? Like, is that the same? Like, how do you know what the equation in that line is? Because it just tells you like dy dx. So it doesn't actually tell you the equation, does it?
This?
Oh wait, you did it like that. Never mind.
Yeah, no, that gives you the numerical derivative at a point. So it gives you the slope of the tangent line at that spot. If you were to draw a tangent line, what's the slope of that tangent line? Right there. And you're right, it does not calculate the derivative for you. You have to do that. Or you could graph it and check.
Menu for 1 in the value bar, that's where you enter the equation, like 3 over.
Yes. All right. Next, look at you. Just perfect people. All right, here we go. These are a little different, okay? Instead of just writing the equation of the tangent or normal line, these ask you something creepy. Find the points. Find the points. So instead of you generating the equation of the tangent line, you're finding that point where we have a tangent line that has a desired slope. Okay? So instead of giving you like when x equals 1, you have to figure out what x equals, right? So what you would do is it always gives you a desired slope, and it's always creepily nested in being parallel to something else or perpendicular to something else. So if something is parallel to the line y equals x, what is the desired gradient? What's the gradient of this thing? 1. So what's the desired gradient? 1, right? So your desired gradient is 1, okay? We have to take that desired gradient and set it equal to the derivative, okay? We're finding the x where we have a tangent line that has a slope of 1, right? So let's expand this out. We have 5x minus x squared. So if we found the derivative of that guy, it would be 5 minus 2x, right? All right, so I'm going to solve. So we have x equals 2. Okay, so that's the x value where it happens, but it wants us to give the point, right? So we can do 2 and plug it back into the original if we want. So we're trying to find the point on the curve where this happens, right? So you can plug it back into the original if you want, or you could plug it.
So is x equals to the x value of where it's parallel or the slope of the line?
I'm going to show you the picture in a second, and hopefully that'll make you like feel good. Why is this coming out like this? Okay, so we're going to find f of 2, which is going to be 2 times 5 minus 2. F f of 2 is equal to 2 times 3, which is 6. Okay, so now I got 2, 6. Okay, so look at this picture. Hopefully this picture is going to give you everything you need to know. We have the original curve, right? Where was the point where we had a desired, is this the right problem? Perfect. This was the last one that we just did. Hold on. T. Is this it? Yeah, okay, so check it out. I was like, okay, this is the original curve, right? And I need to find the point where we have a tangent line that has a slope of 1. So I grabbed the original line just to see if visually these guys are parallel, right? Then I used this tangent line feature, which of course is not perfect. Look at that 0.999. No, it needs to be an x plus 1, which is what we would get if we put it in there. But do you see how at 2, 6, there is a tangent line that has a slope of 1, right? So that's what you found. You found the point on the curve where the two lines are parallel, right? And then I'm going to finish the last problem on the video, and you guys can go back and watch it. And then your homework tonight is going to be doing 7.2 and 7.3 homework, okay? So you got a day off yesterday. Now I kind of get a lot of work tonight.
Could you show me how to type it in my calculator? Yes,
Yes.
I know how to divide. So, menu for...
Wait, what are you asking to evaluate the derivative?
Yeah.
Oh, yeah. What's the point? What's the problem? Do menu for 1. Okay, so what were we evaluating?
He was there literally until
I
he
feel like,
was
I forgot.
Yeah.
Oh, and then you type
And then you
it
type
in.
it in there. Yeah.
I was
All right,
trying to
so-
type it in for like...
Oh my god.
Lucas figured it out, people at home. Don't worry. Okay, so now we are trying to find the point where the tangent to the curve f of x equals x squared minus x is parallel to the line y equals x plus 2. So what's my desired gradient? Well, here's the original equation, right? It looks like we are looking for a desired slope of 1. So we're going to take that desired slope and set it equal to the derivative, which would be 2x minus 1. So now I'm going to solve, and I get 2 equals 2x divided by 2, x equals 1. So when x equals 1, we are going to have a slope of a tangent line that is 1. Okay, so let's find the point on the original curve where that is happening. So I'm trying to find 1 f of 1. I have f of 1 is equal to 1 squared minus 1. So now I have f of 1 is equal to 0. So the point is 1, 0. So let's look at that on the graph. Did I do this one? I did. Okay. So this was the original line that they gave us, y equals x plus 2. And then at 1, 0, is there a tangent line that has a slope of 1? Yes, there is. How fabulous. Okay. Now we're going to try these next 3 problems independently, okay? And we're going to set up the charts by ourselves. So we're going to find the equation of the normal line to the curve y equals the square root of 8 minus x squared at x equals 2. Okay, so if we wanted to set this guy up by ourselves, right, we're finding the equation of a normal line. So we're going to set up point slope equation. Point slope equation. This is how I want you guys to set these up when you're looking for the equation of a line. Okay, so the point is going to be 2 comma f of 2. So let's find when the function is evaluated at 2. 8 minus 2 squared. So this guy would be 8 minus 4, which is 4. Square root of 4 is equal to 2. So I now have a point of 2, 2. All right, so the slope, is going to be the derivative set equal to, for the derivative evaluated at 2. We don't know how to take the derivative of something that looks like this, so we would certainly use our calculator to help us. Okay, so we would have the derivative is of 8 minus x squared, all under our square root, when x equals 2 is going to be negative 1. So we have the slope, or m tan, is going to be negative 1. So our equation is going to look like y minus 2 is equal to negative 1 times x minus 2. And that is going to be the equation of our line. Okay, and that's for the tangent line, but we need to find the equation of the normal line. So this guy's the tangent line. Let's find the normal line, m norm. So that's going to be negative 1 over 1, and then we negate it to make it positive, so the slope is now a positive 1. So the equation of our normal line is now going to be 1 times x minus 2 He's the normal line, and he is our answer. Okay, question 6. It says, consider the curve y equals 5x cubed minus 3x. The curve, has a tangent line at point P, which is -1, -2. Find the equation of this tangent. Give your answer in the form y equals mx plus c. We want to find the equation of a tangent line, so we're going to set up point slope equation to help us answer this question. Okay, so the point is given actually in its entirety, so that's even easier. And the slope, we're going to have to calculate the derivative here. So I've got, I'm going to just kind of scooch this over a little bit so I have more space. Okay. So let's see, I've got dy dx is equal to 15x squared minus 3. So m tan will be that guy evaluated at -1. So I got 15 times -1 squared minus 3. So that guy's going to give me f prime or m tan is equal to 12. All right, so now I've got y minus y1 is equal to m times x minus x1. Does this want the normal or the tangent? Tangent line. Okay, so I've got y minus 2 gives me y plus 2 equals 12 times x plus 1. And then it wants my answer in slope-intercept form. So I'm going to do y plus 2 equals 12x plus 12 minus 2 minus 2. Y equals 12x plus 10. All right. And then for 7, it says find the points where the normal line to the curve f of x equals x to the 4th over 4 plus 5x cubed over 3 minus x squared minus 24 plus x plus 6 is parallel to the line x equals 5. So since we have a find the points type scenario, we're going to do desired gradient. We're going to set that desired gradient equal to the derivative, and then we're going to find the point or points where that happens. Okay, so the desired gradient, well, it needs to be parallel to the line x equals 5. So anything that's parallel to the line x equals 5 will have an undefined
It is now
slope.
2:22 p.m., so the hallway
Right.
should be clear of all students. If you are in the hallway, make
So-
sure you are under supervision of a teacher out of the hallway.
Sorry, I'll wait
And
for
have a
this
great rest of your day.
to go. Okay, so the x equals 5 has a slope of undefined, right? Therefore, the slope of the normal line would have to be 0, okay? So that's a key kind of sneaky understanding, right? The only case where we can't just find the negative reciprocal is when we have a 0 slope and we want to find the perpendicular line. That's going to be a line x equals, or vice versa. If we have an undefined line and we want to find the perpendicular line, that's going to be y equals, and then 0, or it'll have a slope of 0. Okay, so if our desired gradient is 0, what we're going to want to do is take the derivative and set it equal to that 0. So this derivative is a little funky because he's a long one. So I'm going to kind of rewrite this so all the coefficients are out front. Okay, and then now I can take the derivative. 4 over 4 reduces to 1. I now have x to the 3rd plus, oh, this is 5x squared. These are nice. These kind of drop down. Okay. Minus 2x minus 24. Okay. So if I wanted to solve this guy by hand, that would probably take me a while. So instead, what I'm going to do is I'm going to graph the derivative and find the zeros. And the zeros of this guy are going to be, where did I do this? Oh, sorry. I graphed the derivative, which is this blue curve here, and the zeros of the derivative are going to be at x plus 4, x plus 3, x minus 2. That's like what the equation would look like, right? We're going to set that equal to 0 because we're trying to find where this guy has a slope of 0. And we would get x equals -4, x equals -3, x equals 2. All right, so there's 3 points where this guy has a slope of a tangent line that is 0. So where did I kind of write these in? I thought I evaluated these quickly. Oh, I did. So I graphed the original in F14. So I went ahead and evaluated F14 for the 3 points of interest, and I got the following points. Okay. All right, that's it.